So we had started with chemical bonding. We had finished atomic structure and we had started with chemical bonding. And we actually didn't even start. I just wrote sigma bonds, TK, and we're going to study sigma bonds now, which are a type of covalent bond. So the first type that we were studying is how is a chemical bond formed. Remember, atoms have orbitals. The electrons are in the regions around the nucleus, and those spaces that have different shapes. You've got an s orbital, you have a p orbital, you have a d orbital. All of them have, I mean, the area where the electron is going to be found, it has different shapes. So in S and S orbital overlap. Uh, so the example that we are going to do is a hydrogen molecule. It's an H atom bonded to another H atom. So we did discuss this yesterday as well, that if you have two hydrogen atoms, they share one electron each, and that's uh, basically your covalent bond. I mean, what happened was that what basically went on was that you had, just a second. So what happened was that there was one H atom and there was another H atom, and both of them, they needed one electron each. So what they did was that this H atom was trying to pull the electron from this atom towards itself. It's trying to gain the other atom's electron. The other H atom is trying to pull the electron of the other atom. So they're both trying to pull each other's electrons. And what would happen is that the electrons are going to get stuck in the middle, and uh, none of the atoms would be able to gain those electrons, because it's like two people fighting over two electrons. Uh, this atom wants the two electrons to be attracted to its nucleus. This atom wants the two electrons to be attracted to its nucleus. The electrons get stuck in the middle because both have an equal force of attraction. So the two electrons, they get stuck right in the middle. So that's what your covalent bond is, the two electrons getting stuck in the middle. So why is there a force of attraction? There's a force of attraction because the shared electrons, the ones that are stuck, are being attracted by both nucleuses. Or you can say both nucleuses are attracted to the shared electrons. So shared electrons, so there's mutual attraction and there's mutual electrostatic attraction, because the nucleus and the electrons have opposite charges. So mutual electrostatic attraction between the shared electrons, which are negatively charged, and the positive nuclei of the atoms. So that is what the bond is. It's a force of attraction that is existing because both nucleuses are attracted to these shared electrons. So what's an S and S orbital overlap? So you've got one hydrogen atom, you've got another hydrogen atom. Uh, Now we know that electrons, they're not like orbiting the atom. An electron is like a bee; it's buzzing is in a specific space around the nucleus. So the hydrogen atom has one electron, that's 1s1. That's the electronic configuration of a hydrogen atom. The other hydrogen atom is also 1s1. So what is basically happening is that there's one electron, and both of the nuclei have one electron around them, and that electron is randomly buzzing around that nucleus in a occupying a spherical region around the nucleus. This electron also, TK, like a bee, it's buzzing around randomly. Uh, so the electron cloud, that single electron is occupying a spherically shaped region. Uh, so both atoms try to attract the electrons, each of the electrons. The end result is that the two electrons are now stuck in the middle. So they're buzzing around in this area. That's the high probability area now. So previously it was a spherical orbital. The electron was found somewhere in that spherical region, uh, buzzing very, very quickly. So the negative charge was in this spherical shaped area around the nucleus. This electron was also existing in a spherically shaped region around the nucleus. When there was mutual attraction, this atom started attracting the other's electron. This one started attracting the other hydrogen atom's electrons. The electrons get stuck in the middle. So they're now buzzing around in this specific area over here. So the way this overlap is shown is that you have two spherically shaped regions. This one has one electron, and this other one also has one electron. So the electrons buzzing around this, there's an electron that's buzzing in this area over here. They both attract each other's electrons, and there's going to be a new bonding orbital. Where would the two electrons exist between the two nuclei? They're going to be somewhere in the middle. They would be buzzing around in this specific area, somewhere in this particular area, right in the middle. So the orbital would change. The two orbitals are going to merge because the orbital is the place where you're going to find the electron. So now the electron would be found. So now the electron is going to be found in the middle somewhere. So that's your new bonding orbitals. The two orbitals have merged. Remember, an orbital is the space or the region where there's a high probability of finding an electron. So it's no longer the spherical region over here. It's no longer the spherical region over here. The two electrons are stuck in the middle. So that's where there's a high probability of finding the two electrons. So that's your bonding orbital. That's known as a sigma bonding orbital. So is this clear to everyone? Or known as a sigma bond, basically. Is this clear? And is this clear? Alicia, Abdullah, is this clear? Aisha?
Sir,
Yes.
I don't understand how they'd be attracted to each other if there's a positively charged nucleus. Wouldn't it repel?
Remember the electrons. What is the charge on electrons? Like if I rub this off,
They're
so
negative.
here's a nucleus over here, right over here. 1 second. So here's your electron, right? Let me highlight that. So this is your electron that's buzzing in this area, right? And here's your nucleus over here. This nucleus over here is going to try and pull that electron towards itself, right? Is that clear? I mean, they're negatively charged, right?
Yeah.
And the same would happen over here. There's an electron that's buzzing in this area. So, I mean, that electron is randomly just buzzing around in a spherical region. The other atom's nucleus is over here. It's going to try and pull that electron towards itself. So, I mean, both atoms are trying to pull those electrons, right? So the electrons kind of get stuck in the middle. They're now going to exist. I mean, they would be buzzing around somewhere in this area. They will be stuck in this area because this nucleus is attracting it. This nucleus is also attracting it. It's like two people fighting over electrons, and the electrons are going to get stuck in the middle. Is this clear?
Yes, thank you.
So the two regions are going to mix. Basically, the two electrons are going to mix up. And so an s orbital overlaps with an s orbital. That results in an s and s overlap. That's basically your sigma bond, which you can see over here. Okay, is this clear? Mayim, is this clear?
Yes.
So that's an s and s overlap. Now electrons can exist in all sorts of orbitals, right? Now D is not in your course, so we can let that go. Not yet, it's in A2. But we can talk about the p orbital. So a lot of times what would happen is that there's going to be an s and p overlap. So orbital overlap number 2. That's another type of sigma bond. That one is an s and a p overlap. And what happens in an s and p overlap? You basically need atoms where one atom has an s orbital, the other one has a p orbital. So for example, we have an HF molecule. Now H has just one electron, it's just 1s1. F has a lot of electrons. F has 9 electrons, so the electronic configuration is 1s2, 2s2, and 2p5. If I 2p subshell has three orbitals, 2px, 2py, and it's got 2pz. So 5 electrons means there's two, there's one. So I'm just going to focus on the empty orbital. I'm just going to focus on this one and this one. Because if F, I mean, all the other orbitals are completely full, so F cannot attract electrons on the other in the other orbitals. The other orbitals will not be involved in bonding because they're already full. I mean, they can't accommodate any electrons. So if F is the nucleus of the F is going to attract an electron, it's going to put that electron in the 2pz because that's the one that's half filled. That's the one that has room to accommodate an extra electron. So I'm just going to draw the empty orbitals that are partially filled that can accommodate electrons. So again, H, the electron is in a spherical region around the nucleus. So the electron is occupying this spherical area over here. That's H. F, on the other hand, ignore all the others. TK, I'm just ignoring them. Because they're already full, they wouldn't be involved in bonding. I'm just focusing on the 2pz. Now it's a p orbital. P orbital is dumbbell shaped. So around the nucleus, there's going to be an electron that would be so there's going to be an electron that would be existing in this dumbbell shaped orbital. Let me just so it would be existing in two lobes around, sorry, it would be existing in two lobes around the nucleus. So the electron would be very quickly buzzing in these areas, randomly just moving in these two orbitals over here. Not two orbitals, this is one orbital. So the electron is buzzing around this area. This electron is buzzing around in this spherical area over here. Both orbitals have room to accommodate one more electron. So the same thing would happen. You've got fluorine over here, and this fluorine would try to fill its orbital. It's going to try and pull somebody's electron and fill this up. So it sees hydrogen's electron. It's going to try and pull that and try and gain that. Hydrogen needs one electron, so hydrogen would do the exact same. It's going to try and pull the electron of fluorine and try to keep it with itself. The end result is that the electrons are going to be stuck somewhere in this middle area over here. And the two electrons, both atoms are trying to pull each other's electrons. The electrons are going to get stuck in the middle over here. No one would be able to gain those electrons. So you would have to change the bonding orbital now because the two orbitals are going to mix up. So here was your fluorine. Now the maximum electron density is again right in the middle. So fluorine's orbital gets pulled and stretched in this direction over here. This other lobe would become really small because the electron over here is getting pulled by the hydrogen over here, so it's not going to go in that lobe over here. So this lobe would its size would decrease. There would be very little chance that you'll actually find an electron on this side because that electron is getting attracted to the hydrogen. Hydrogen's electron is getting attracted to the fluorine. So this lobe would shrink. The area would shrink. And the area in the middle, that's where there's going to be maximum electron density. That's where there's going to be maximum probability of finding electrons. So that's your S and P overlap. That's what it's going to look like. So is this clear?
Yes, sir.
Yes, sir. Yes.
So then we can talk about number 3, which is a P and P overlap. So let's talk about 3, which is P orbitals overlapping. Now the example for that can be an F2 molecule. So two F atoms bonded to each other. We already know that F has a 2pz orbital. I mean, all the other orbitals are kind of full, so we can ignore them. It's got a 2pz orbital that needs one electron. The other F is exactly the same. All the other orbitals are full. It's got a 2pz orbital that needs one electron. So you've got a fluorine atom with its 2pz, an electron buzzing around in this space over here, and you've got another fluorine atom which would be over here. So an electron would be buzzing around in this area over here. Uh, both orbitals are empty or half-filled. They would try to fill them up. This fluorine would try to attract. They would try to attract each other's electrons. And again, the maximum electron density would now be somewhere in this middle area. Both atoms trying to pull each other's electrons. So that's the area where now there's going to be maximum probability of finding the electrons. The electrons are going to get stuck over here. And there would be very little chance of finding electrons over here or over here. So the new bonding orbital or the new region where there's going to be maximum probability of finding electrons is going to be this middle area over here. So this area would increase in size. The side lobes would shrink because there's going to be very little probability now of finding the two electrons on the sides. So most likely the electrons are going to be found somewhere in this middle part over here. There's one nucleus, there's another nucleus, and the electrons are probably going to be found somewhere in the middle. So is this clear? Is this clear? Hania, is this clear? Mayim? Abdullah, is this clear?
Yes, sir.
So now, so you have to remember, you'll be asked to draw them. There's going to be an SNS overlap, there's going to be an SNP overlap, and there's going to be a PNP overlap. Some properties of sigma bonds. Some properties of sigma bonds, like how do you identify sigma bonds, or how do you describe sigma bonds? So sigma bonds are that the electron density, number one, electron density or the probability of finding the electron, it exists exactly between the two nucleuses. You have one nucleus, you have another nucleus, the electrons are like stuck in the middle, right in the middle. Not exactly in the middle, but on the axis connecting the two nuclei. So electron density lies between, or a better word would be lies on the axis connecting the two nuclei. So you've got one nuclei and you've got another nuclei. The electron density is always right in the middle. Uh, so that's one property of a sigma bond. Then another property is that we're going to study in a bit more detail just in a short while. That is that whenever you have a single bond, see, so whenever you have a single bond, that's always a sigma bond. ठीक है, whenever you see any molecule, ठीक है, any random molecule and see a single bond, that's a sigma bond. An example is like if I have, I mean, like I can draw the example over here. So an example is like if I have a methanol molecule and there's sorry, ethanol, and there are all sorts of bonds, right? Now all of these are sigma bonds because if you focus or focus on any of the bonds, the electron density is right in the middle. There's one nucleus, there's another nucleus, the electrons are stuck right in the middle. So that is a sigma bond. Here's another sigma bond. You have one nucleus, another nucleus, the electrons are kind of stuck in the middle. I mean, the two orbitals are merging and the electrons get stuck right exactly in the middle. So every time, whenever you see a single bond, that is by default a sigma bond. But what happens when you have a double bond? Whenever you have a double bond, then that is one sigma and two pi bonds. We haven't studied, sorry, not two pi bonds, that's just one pi bond. So that's one sigma plus one pi bond. So we haven't studied pi bond yet. Whenever you see a triple bond, that is one sigma plus there are two pi bonds. So the basic idea is, I mean, forget pi bonds at the moment, but the basic idea is every time when atoms bond, the first bond that is formed between atoms, always between atoms, is always going to be a sigma bond. Any bond that's formed after that, like you got a double bond. So if there's another bond that's being formed between the same two atoms, then that's going to be a pi bond. If it's a triple bond, then the first one was a sigma, the rest of the two are going to be pi bonds. So every time an atoms bond, the first one is a sigma bond. I'll clarify this later on, and there's another property which I'll clarify in a short while, and that is that rotation is possible around a sigma bond. What I mean by that is that your molecules are like complicated structures. It's what does rotation mean? So here's a molecule, and the molecules are three dimensional. There's an OH. Uh, this shows a bond that's coming out of the page. This shows a bond that's going into the page. So it's a three-dimensional molecule, and over here I've got an H and a Cl. I'm focusing right now exactly at this sigma bond. You can forget the detail, it's a sigma bond because it's a single bond. There's a nucleus over here, there's another nucleus over here. The electron density is right in the middle. So the electrons are kind of stuck exactly in the middle. It's just like the same sigma bond. Right now, we're not sure whether it's an SAP overlap or a PNP overlap, but the basic idea is the same. That the electron density would be right in the middle of the two nuclei. Whether it's a PNP overlap, it's the same thing. You've got one nucleus, you've got another atom's nucleus, and the electrons are exactly in the middle. So the shape can be different, but the basic idea is the same. That the electrons in a bond are right in the middle. So what I mean by rotation is that a sigma bond is not going to. This is a sigma bond. It's not going to restrict rotation. Imagine this as two wheels uh, of a car connected to each other. Like these, I mean, think of these as spokes that are coming or connecting the wheels. This side could rotate independently. Like if I want to rotate this side, or then this side can rotate. The bond is not going to break. Like even if the OH is pointing upwards, I can sort of twist it around and I can bring the OH downwards. The nucleus is still there, the electrons are still there, and the attraction is still there. So the bond is not, it's not going to break. So, so think of these as spokes coming out of this carbon atom. Uh, Molecules can twist around. Their bonds can point in different directions. No matter how it rotates, this bond over here is not going to break. The attraction would still be there as long as this nucleus is still there. This nucleus is still there. The electrons are still in the middle. Uh, no matter if this part rotates, the OH is pointing upwards, it starts pointing downwards. It will not affect the bond that's over here. It's not going to break. So is this clear? Like the two sides can rotate independently. Is this clear or not?
Yes, sir.
Okay, let me see if I can, because it's a three-dimensional thing. Let me show if uh, to use some. I mean, this is the closest I can find. So there's a bond over here. So you can see what he has done is he's colored the H atom. So what we mean by this is that think of this as a wheel. You can twist it around. The H could, I mean, you can bring it down. You can rotate it. The bond would still be there. It's two electrons. The nucleus is still there. This nucleus is still there. So the attraction is still present. It's not going away. So rotation is possible around a sigma bond. I think this. So this one is also showing this. These bonds, I mean, ignore these bonds. I'm just focusing on this sigma bond over here in the middle. Uh, this side can rotate independently. This, I mean, the bonds can point wherever they want to point, and you can twist them around. The bond would still exist. It's not going to break. So, so this is what I mean by rotation. And when we talk about shapes of molecules, we're going to talk about that in a bit more detail later on. Let me just copy this as well. And we can cut this out. I said those are properties of sigma bond. So we're going to do some more examples. Remember, whenever a single bond is formed, that's a sigma bond. So let's try and figure out how water molecules are going to bond. So an example is H2O. So let's try and draw how those sigma bonds are formed. H2O has single bonds, so that means both of them are sigma bonds. So the first thing is you write the electronic configuration of oxygen. Oxygen has 8 electrons. So that is 1s2 and 2p4. 2p4 means it's got 2px, it's got 2py, and it's got 2pz. So it's 2, 1, and 1. Now, two of the orbitals are empty. It needs electrons in two of the orbitals. There's 2py with 1 electron, 2pz with 1 electron. All the other orbitals are empty, so they don't need any bonding. They're not going to attract electrons. It's only the 2py and the 2pz that have some space available to attract electrons. So I'm going to draw just the 2py and the 2pz. Now that means there's a p orbital on the y-axis. Let's imagine this is the y-axis. And there's a p orbital on the z-axis. So there's an electron there's a single electron that's buzzing in this area, and there's a single electron that's buzzing in this area over here. So remember, they're two totally different orbitals. So how many hydrogens bond to it? Two hydrogens. So there's going to be a hydrogen atom that would be coming along with its spherical orbital, the electron buzzing around in the spherical orbital. It's going to bond with one of the p orbitals. It's going to try and attract its electron. This p orbital would try to fill itself up by attracting the other's electron, and the electrons are going to merge, and the electron density would be maximum in this space over here. Then another hydrogen would come along, and that hydrogen also has 1 electron, and you've got a p orbital that has 1 electron. The electron is buzzing in these areas over here and over here. So the hydrogen's nucleus is going to try and pull that electron. So that electron will get attracted to the hydrogen nucleus, and they're going to start overlapping, and the electron density would be maximum in this area over here. So oxygen's 2 electrons, which were lying or existing in the p orbital, they're going to be pulled by one hydrogen atom. The other one would be pulled by the other hydrogen atom. So oxygen will have two SNP overlaps. So this is an oxygen atom. This is a hydrogen atom. It's going to be, so this is your hydrogen atom. The other lobe would become, it's going to shrink. It's going to be a p orbital overlapping with an s orbital. So this side, the electron would hardly go to this side. So this side would shrink, and the electron density, maximum electron density, would lie in this middle part over here. And then there's going to be this P and S overlap. So again, the same thing would happen. That there's going to be a hydrogen atom over here, and the electron density would be maximum in this middle part over here. So there would be two S and P orbital overlaps. This over here is your oxygen atom. So oxygen had two orbitals. One electron gets pulled in by one of the hydrogen atoms. The other electron gets pulled by the other hydrogen atom, the second hydrogen atom. And as a result, you get two S and P overlaps. There's one sigma bond, and then there's another sigma bond. Sigma is also referred to as the Greek symbol sigma. So you're forming two sigma bonds. Is this clear? Rubab, Nabila, is this clear? Mariam, Hania, is this clear?
Yes, sir.
So two S and P overlaps. Let's do another one. Let's talk about an Nf3 molecule. So an Nf3 molecule, it's N going to be forming three bonds with fluorines. Like N forms three bonds. So N's electronic configuration is, it's got 7 electrons. So it's 1s2, 2s2, and 2p3. So that means the 2px is half filled, it needs 1 electron. The 2py is half filled, it needs 1 electron. And the 2pz is also half filled. So each one of them, they need 1 electron each. So that's 7 electrons. And each one needs 1 electron. Fluorine has 9 electrons, so its electronic configuration is 1s2, and then all the other orbitals are full except for the last one, which is the 2pz, which is 1. So fluorine just has to fill this 1 electron over here. So if I draw nitrogen, now nitrogen is going to be three-dimensional. It's going to be a three-dimensional. It's got 3 orbitals all on different axes, x, y, and z. It's got 3 p orbitals all lying on different axes. So there's going to be x-axis, there's going to be y-axis, and there's going to be a z-axis. So 3 different axes. 2px, 2py, and 2pz. All the other orbitals are full, so they won't be involved in bonding, so not drawing those. So an electron on the x-axis, just one, buzzing in this area. There's an electron on the y-axis, and there's an electron on the z-axis in a spherical area over here. So each one of the p orbitals, 2px, 2py, and 2pz, they need electrons. Each one of them, they need electrons. So fluorine is going to come along, and a fluorine atom has just a p orbital. So that means so just drawing fluorine's p orbital, it also has 1 electron. So they're going to try and pull each other's electron. So they're going to try and pull each other's electron. So fluorine's p orbital, this 1 electron is in this area. They would try and pull each other's electrons. So the end result would be the electrons are going to get stuck in the middle, and that's a fluorine atom. This is a nitrogen atom. Same thing happens over here. There's another fluorine atom, and exactly the same thing happens. The fluorine atom has just one of the p orbital that it needs to fill up. So it tries to attract the electron from the nitrogen atom. Nitrogen tries to pull its electron, and the electrons are going to get stuck in the middle of the fluorine and the nitrogen atom. And the last one as well, you've got another orbital of nitrogen that needs 1 electron. So this one another fluorine would come along with its p orbital that needs electron, tries to pull it. They both, and the electrons get stuck over here in the middle. So it's basically p and p overlaps that are happening. There's a p orbital over here that overlaps with fluorine's p orbital, another p orbital of nitrogen that overlaps with another fluorine p orbital. So three different sigma bonds are getting formed. There's a sigma bond over here, there's a sigma bond that's formed over here, and there's a sigma bond that's formed over here. So if I try and draw a neater version of this, so the electron density is now between the nitrogen and fluorine atoms. This lobe would be smaller now. This other lobe would also be smaller. The two electrons are going to be stuck in the middle. I've drawn this orbital over here. The other one, it's going to be exactly the same. So the two electrons are going to be stuck in this middle area over here. And then there's going to be a third p and p overlap. And the two electrons will be stuck in this area over here. So there would be three sigma bonds that would be formed. The three sigma bonds, all of them are like this. It's like a p and p orbital overlapping. One atom has a p orbital, the other one also has a p orbital. Both of them are incomplete, so they start merging up and they start overlapping. So this is how a nitrogen atom would form three sigma bonds. Is this clear?
Yes.
TK, everyone else, is this clear? Any questions? Hania, is this clear? Aisha? Lisha? Mayam?
Yes, it's clear.
So, but in your question, you'll just be asked to draw one sigma bond. So that I mean, this is just maybe they might ask you to draw two sigma bonds. But just get this idea clear that most of the time the question is remember every single bond that's a sigma bond. Whenever you see single bonds, that's a sigma bond. Why is nitrogen forming three sigma bonds? Because it's got three orbitals that need to be filled up. So electrons from some other atom would try to fill those up. Like there's a fluorine that's trying to fill this electron. I mean, nitrogen is trying to pull its electron, but it's not able to, so the electrons are over here. Another fluorine atom has one electron. Nitrogen tries to pull it up, pull its electrons, tries to fill it up, but the electrons get stuck in this area over here. And same is the case with this fluorine, that it tries to attract the electrons and the electrons are stuck in this area. So three different sigma bonds are formed, and what you just most likely what you're going to get a question on is this thing. They'll just ask for you to draw just one type of sigma bond. It's either going to be, you just have to figure out whether it's an S and S overlap, or whether it's an S and P overlap, or whether it's a P and P overlap. For example, if they ask you to draw one sigma bond of an HCl molecule, so you should know that in HCl molecule, H is 1s1 and Cl is in group 7. That means even if you write the whole electronic configuration, it's going to be all the other orbitals are full. 2p6, 3s2, 3p5, that means 3px, 3py, 3pz. So it's 2, 2, and 1. So it's a p orbital that needs an electron. It's an s orbital that needs an electron. So they're going to try and pull each other's electrons. So it's going to be an S and P overlap. An S and P overlap would look like this. S would be spherical, P would be double shaped. So at the end of the day, it's probably going to look something like this. Like you had a p orbital, electron in a p orbital, and you had an s orbital, electron was in an s orbital. Now the two electrons are going to merge up, they're going to mix together, and this is what an S and P overlap would look like. Is this clear?
Yes.
So let's continue tomorrow with pi bonding now. Okay, let's continue tomorrow. Okay, everyone, take care. Allah Hafiz.
Okay, so thank you. Allah Hafiz.
Allah Hafiz.